Okay, I'm Rick Fleeter, and I'm going to talk first about microspace, basically what it is. There's more to why we don't see more activity in more revolutionary forms of space, and that's because space as an industry is an ecosystem. Every industry is an ecosystem, and you have many, many engaged parties who want the system to remain the way it is. And if you look at any industry that has revolutionized its environment, there is a struggle involved. It's natural that people want to protect what they've built, the companies they've built, the jobs they've built, the missions that they've built. And in a way, we have a system that picks what deserves merit, what deserves funding, and where do those people get their ideas? Where was their... So one of the reasons that I need to do education in space, that we need to talk to 18-year-olds and 20-year-olds and 22-year-olds about microspace, is that until those people are the decision makers, we can't really expect decision makers to choose microspace. It's not wasn't their thing. What the slide is talking about is that big rockets are much cheaper per kilogram than small rockets, and that bringing things back from orbit is particularly challenging and particularly expensive. So one of the things that normal people want to do with space, normal people don't want to launch things into space and never see them again. They want to launch a specimen into space and then bring it back. We tend to not do those missions for a very simple reason. They're very expensive. So without really thinking about it, we limit ourselves away from doing those missions because we're thinking, gee, it's really difficult to bring things back. It's almost more difficult to bring them back than it is to launch them, right? Because where are they going to come back? So how do you plan that reentry? And how do they not get burned up? And then are they splashing into the ocean? And how do we know it's going to land in the ocean? Then if it does land in the ocean, like we have to get ships? Or how the heck are you going to get the thing out of the ocean? If we don't crash it into the ocean and we land it on land, how do we know the parachute's going to open? How do we know it's not going to make a gigantic hole in someone's house or office? Or, it's not an incoming missile. I mean, there's a lot of problems with bringing things back from space whole, in pieces. So we just eliminate that. We just develop a blind spot and we say, look, we're not doing that. Except for maybe the big missions, we bring astronauts back from space. But the idea of bringing biological samples back from space, other than when the astronauts come down from the space station, is not really part of the picture, simply because of the way transportation works, not because it's not a good idea. So let's talk about launching a little bit, because what we've done over the last 50 years is tried to convince ourselves that launching was expensive simply because it was bureaucratic, and that launch vehicles were built by big governments, and big governments don't do things efficiently, and that we needed to change basically the management structure of how launch vehicles were built. And now we've been trying that for about 50 years. And on the US side, about $1 billion has been invested in the idea of making small, low-cost launch vehicles with basically no positive result and a few fairly negative results. And what do I mean by negative results? Because, in fact, we have Pegasus, right? And Pegasus is a small launch vehicle which came out of that culture of let's let private companies build launch vehicles and that will make them smaller. And this was, in a way, why am I talking about this? For two reasons. One is launch becomes the design constraint from the satellite. And so that makes launch fairly important to us, to act like there's no launch environment out there and I just want to build my satellite. Obviously, you're not going to get into space that way. But the other reason is that it was an incorrect extrapolation of the idea of microspace. Microspace was a very attractive idea in the era when Pegasus was proposed. And the idea of Pegasus was it'll be just like a small satellite, okay? And therefore, because small satellites are small and cheap and they don't have to worry too much about reliability and blah, we're going to do the same thing in rockets that we've done in small satellites. And because nobody understood what was the magic that made small satellites work so well, they incorrectly applied that analogy to the Pegasus rocket. And what was the result? The results were a lot of failures because, in fact, the Pegasus rocket is not a small, simple device with a relatively small number of moving parts that didn't have to be highly reliable. In fact, it's a very large, tens of thousands of kilograms type gadget that has a lot of active parts in it, each one of which has to work very precisely, and it does need to be built in a way that pays the tax of reliability. But more importantly than that, when Pegasus was proposed, it was going to be $6 million to launch 350 kilograms into low Earth orbit. And in fact, the cost of Pegasus now is between 5 and 10 times that number. The actual realized repeatable cost of Pegasus is almost 10 times what the promised cost was back then. Okay, so that was Pegasus, and then there were a million excuses. Well, it turns out to be fairly expensive to launch things from airplanes. You need that wing thing to make the turn, et cetera, et cetera, et cetera. And along came SpaceX with the Falcon. And it was, for those of us who lived through both, it was a little bit of deja vu, because the Falcon 1 came out saying, well, we're going to launch 350, 400 kilograms into space for $6 million. And I was like, okay, where have I heard that number before? So where is the $6 million where's the $6 million SpaceX Falcon 1 today? It doesn't exist. And why doesn't it exist? Well, I did that study for a space agency, not the US space agency. What's the magic of SpaceX? How do they do those incredible $6 million launch vehicles? And the disappointing answer was, we want to know, because we want to do exactly what they did. It's a very logical question. The answer was, they don't do it. They can't do it. They discovered the same thing that Pegasus discovered. It's very difficult to just change the management structure and thereby change the physics. Okay, so after this failure of 50 years of trying to make this low-cost small launch vehicle, where do you go for answers? What do we have to do at this point? Well, I mean, you can turn yourself back to basic physics, right? And this slide says size matters. Transportation systems are very sensitive to scale. As you make them smaller, they become less efficient. So I have various comparisons on this slide. A car, in terms of how many euros it costs to take a passenger, it's kind of mixed units because I did it in miles, right? But how many euros it takes to take a passenger a mile in a car is about 5 times what it takes to do the same thing in a bus, in a touring bus. If you take a very small boat, which in the US would be called a Boston whaler, a little fishing boat for 3 or 4 guys, how much does it cost in euros to take those people a mile over the water? Compare that to the Queen Mary, humongous luxury craft with restaurants and bars and hotel rooms. All of those things do not exist on a Boston whaler. A Boston whaler has seats and a motor. You would think the Boston whaler would be very economical. It is economical. You can buy the boat for a couple $1,000s, and yet per passenger, the Queen Mary is approximately half the price. Notwithstanding that you've got the grand pianos and you've got the gourmet food and you've got air conditioning and you've got satellite TV and all that kind of stuff. I mean, the thing is a floating luxury hotel, and notwithstanding all that, it costs half of what roughing it on a Boston whaler costs. Boston whaler doesn't even have, you know, a sunshade. You're just out there on the open water. Okay, Learjet, right? Small jet, nice. It's fancy. I mean, if you can get a chance, I've had a chance a couple times in my life to be a passenger on a Learjet. It's excellent. 4 people in jet, 2 crew. You go when you want to go. You arrive at the airport. They start the engines, and there you are at your destination, and you get off, and you're right where you want to be. No changing planes, no nothing. Fantastic. Why doesn't everybody do that, right? That's much nicer than going to the airport and going through security and checking your luggage and blah, blah, blah. Well, because the Learjet costs about €1 per passenger mile, and even a small transport jet like a Boeing 737 that holds like 160, 180 people costs approximately 1/10 as much per seat mile. If you get in a jumbo jet, you can, you know, one of the big Airbus 340 type things, the old Boeing 747, that kind of plane, that's another factor of 2 cheaper. So it's 20 times more expensive to fly in a Learjet. And that's why we don't take ourselves all over the world in Learjets. Okay, let's stop talking about analogies and talk about rockets. How much do rockets cost? Okay, to make all these things fit on the same slide, I had to divide the cost, not per passenger, but per kilogram, which is roughly 1/70th of a passenger or 1/100th of a passenger if you take some life support with them. I had to divide it by 2,500 just to fit on the same graph. So we're already talking about something that costs between 2,000 and 200,000 times more than an airplane ride on a Learjet. So it's expensive, right? But what's the ratio? A Pegasus costs about 2,500, okay, let's say euros for a unit of launch, like a kilogram or a fraction of a kilogram, whereas an Ariane 5 costs about 10% as much. It's very similar to the analogy between a transport jet and a Learjet. And why is that? Because no matter how small your rocket is, it still needs a guidance system. It still needs stage separation systems, whether the stages are big or small. It still needs a command destruct system. It still needs a fairing, and the fairing has to be able to open, and then it needs a payload ejection mechanism. It still needs to be tracked from the ground. It still needs to be fueled. It still needs to rent space at a launch center. It still needs everything. You have to call all the various space agencies of the world and tell them when you're going to launch it so they don't think that the Americans are launching a missile into, Russia or something like that. Everything is the same, it's just smaller, okay? So is a small fuel tank really that much cheaper than a big fuel tank? Not really. And how much of the cost is really in buying a fuel tank? I mean, none. So in fact, the Pegasus costs almost as much as the next bigger rocket. And nowadays, the Pegasus costs about as much as the smallest Delta used to cost when they were launching it. And the smallest Delta was launching almost 10 times as much payload. So the efficiency is just not there because the scaling doesn't work for small launch vehicles. So does that mean we can't have small satellites because we don't have small launch vehicles? Well, obviously we solved that problem in air transport. You organize 400 people who want to leave at the same time from Fiumicino and all arrive in Cairo at the same time, and you divide up that launch between 400 people. That's a little harder to do in space because you don't have thousands and thousands of missions wanting to leave every single day so that you can somehow manage the logistics of all that. But what I would say is we really don't have a shortage of launch space. What we have is a shortage of distribution of launch space. Every week, large rockets are launched into space. Every time they launch them, there's a certain amount of excess payload. And how much is that excess payload? I mean, on a 5,000 kilogram launch, it could be 50 kilograms, which is kind of a throwaway, 1%. But for us, that would be 50 microsats, 50 CubeSats, or at least 40 CubeSats plus the ejector. And we don't use it. We don't ever use it. Every week we could be launching 50 CubeSats, but we're not launching 50. That's a lot of CubeSats, right? That's 2,500 CubeSats could be getting launched a year, but we don't launch any that way, 0. So what's the problem? The problem isn't that the launches aren't there, that the mass isn't available to take us into space. It's that we don't have a distribution system, right? You read about people who are starving in Africa. Is it because the world doesn't have food? No, there's tons of food, but it's not distributed into Africa. There's places in the world where people don't have water, right? And the water that they do have is highly polluted. Is there not enough fresh water in the world? There's tons of fresh water in Canada in the Great Lakes. I'm from the Great Lakes. These are enormous bodies of water that look like oceans. They're filled with fresh water, and then they just tumble over Niagara Falls and go up the St. Lawrence Seaway and dump into the Atlantic Ocean because there's no use for it. There is a use for it, but it's on the other side of the world, and we don't have a distribution system to take water. So, okay, going back to launches, how would we do that? And the next slide is about that. One of the problems with geosynchronous orbits is how do you get there? You go to geosynchronous transfer orbit, which is an elliptical orbit, apogee at 40,000 kilometers, perigee typically 400 kilometers. Used to be lower, but for stability reasons and other reasons, we use higher perigees now. Okay, so whatever. The problem is nobody wants to be in that orbit. It's not even really a very stable orbit. And anyway, it's a difficult orbit to manage your spacecraft because either it's 40,000 kilometers away near apogee, or it's 400 kilometers away and going at an incredible velocity. So you have this gigantic Doppler shift and virtually no time to talk to the satellite when it's in low Earth, in the altitude of low Earth orbit. And you could never make meaningful photographs because it's moving so fast and the orbit altitude is changing so dynamically. It's a useless orbit. It's only useful as an orbit as a first step to getting to geosynchronous transfer orbit. But you could use it a different way because when it's at perigee, it's seeing the atmosphere a little bit. And if you take energy away at perigee by atmospheric drag, what's the result of that? You lower the velocity at perigee. Therefore, when the satellite comes around to the apogee is actually lowered. Every time it passes through the atmosphere, the apogee is lowered. It's like, gee, Rick, we obviously know that because that's how we do atmospheric capture at Mars. We send this probe out to Mars, and it goes into a highly elliptical orbit around Mars, which it reaches by scraping through the atmosphere of Mars, which takes some of its velocity away. And then every subsequent pass through the atmosphere, the apogee is low. So we do it on Mars, but we don't do it on the Earth. It's kind of ironic in a way. So all you really need to do is add to your Peapod a big parachute, right? And every time that parachute goes through perigee, the Peapod is getting lower and lower and lower. At a certain point, the apogee is where you want it, right? Like 400 kilometers or 500 kilometers. Maybe the perigee is too low. The apogee is at 400, 500 kilometers, but the perigee might be too low. In that case, you need a little bit of propulsion to raise the perigee, and then you're in a circular orbit. So with a relatively few number of meters per second, like 10, like 20, like 30 meters per second, which is an attitude control system, you can go from geosynchronous transfer orbit to low Earth orbit. So why don't we do that? Because we're off solving this problem that we dream about of building a small, low-cost launch vehicle, but the physics are that that's not going to happen. It's not going to happen until technology radically changes. I have nothing against spending money on looking for radically different technologies, water rockets, laser rockets, but those things are not realizable right now. So in the meantime, we should work on the distribution problem. Take the launches that we do know and the large launch vehicles that are in fact highly reliable and highly efficient because of their massive size and leverage that. It wouldn't be that difficult. It's more a matter of the will instead of the way, as they say in English. This idea that, not to beat up on this problem too much, but I have a slide on the SpaceX Falcon, and let me just summarize that slide, which is on one piece of paper, you can estimate the cost of a small launch vehicle, and that's what this slide basically does. And then it references a rather large study done at MIT and at the Sloan Business School on what is the very minimum cost that a small rocket could require to be a sustainable business where the price of launching is approximately equal to the cost of launching, so that you're not having to subsidize every significant launch. And their answer was $25 million just to break even, basically after the initial investment has been recuperated, which means to recuperate some of the investment, you're talking 20, 30, 40, 25, 35, $40 million, which is exactly what Pegasus costs. And that's exactly where the Falcon 1 was going to cost when it was basically canceled. If you call SpaceX and ask them why the Falcon 1 doesn't exist, they say there was no demand for it. How is that possible? There's all these small satellites. There's 60 small satellites being launched every year. Everybody wants a small launch vehicle, but they don't want it at $30 million. They want it at $1 million, and that's impossible with the current technology. So why does all this matter? Why am I talking about microsatellites and spending 15 minutes talking about transportation? Because, do the analogy again with jet travel, right? We're used to being able to fly places, and how much does an airline ticket cost? Okay, there are places that advertise they don't cost anything, right? Promotions from Ryanair, let's eliminate that. You can get on an EasyJet and fly from Rome to some second-tier airport in England for about $99, 129 euros, some number like that, which, you know, all of us have probably done many times. And that enables us to go on vacation. Oh, I want to go, I have 4 days, what the Italians call a ponte, I have a long weekend, and I'm going to go to England and visit friends of mine in England, or I'm going to go to Sofia, Bulgaria. It's not very expensive to come here, particularly if you buy a low-cost ticket on an off time, out of season. You can do it for 99 euros. Fantastic. What if that ticket were, instead of 100 euros, 100,000 euros? All right, because that's what we're facing in the launch world. We're facing a cost that is 2,000 times more. So instead of 2,500, some weirdo number like that, thousands of times more. So let's say that it's, you know, 1,000 times more. Airline ticket is not $100 to $1,000 really. Let's say it's $100,000, not out of the question, right? Would airlines exist? How many people would be buying those tickets for $100,000? Would you be going on vacation to England for $100,000? No, I wouldn't be either. And neither would any of the other people that you're seeing in the airport. We'd all give it up for $100,000. I mean, you might do it once in a lifetime, which sounds a lot like going into space. Very wealthy people do it once in a lifetime. That's the model. Okay, so, all right, you wouldn't be able to go on vacation. Would DHL exist? Would there be Amazon.com if there were no airlines? How fast could you get that book from Amazon.com? You might as well just order it at the bookstore, right? And would the air traffic control system exist that manages thousands, hundreds of thousands of flights globally every day? Would Federal Express and DHL exist? No. What about all the airports? Would the airports in Bristol, in Bergamo, all the second-tier airports, would they exist? Who would be flying out of those airports? Nobody. So there would be a few airports, and who would be flying out of those airports for $100,000 a ticket? Governments, mostly for military missions. If you absolutely had to do this flight in order to save your country, sure, you'd buy 10 tickets, even 100 tickets. It's affordable for a government to spend $10 million on some airline tickets. Okay, so who would decide who got to have those 100 airline tickets, right? The government would decide, because they're the only ones who can afford it. So we would go from this economic model that we have of millions of people going on vacation all over the world, Americans going to Rome, Romans going to Boston, and we would replace all that with military bases where there were airline flights taken by very few courageous people that we would call something like astronauts for only very specific things that the entire society would get together to fund them. And that would be how airline travel would look, just for a factor of 100 to 1,000 in the increased cost of the ticket. And then, would we have the United States as we know it today? Would it be practical to have a country 5,000 kilometers across? Because there's no way to get across the country. Those people on the other side, it would take you weeks to go and visit them, right? So our entire way of life, I mean, Americans are used to sending their kids to school in the other part of the country. I grew up in Ohio, went to school in Rhode Island. It's 1,000 kilometers away, no problem. If I want to get home, it's an hour on the airlines. But if I had to take the train, it's 24 hours on the train. So a lot less kids would go to college 24 hours away, let alone my roommate who came from Los Angeles. That's 100 hours on the train. If you can even find a train that does that, maybe 120, there's no way that guy would have gone to school, and no way we would have met, and no way all those interactions would have happened. Okay, how about the road trip? If gas were $500 a liter, right? 100 euros a liter even. And what if a car, instead of costing 10,000 euros, cost 1,000,000 euros? Okay, would there be production lines for cars to drive the price down? No, because there wouldn't be anybody buying those cars. So you'd be building a few cars a year, probably to spec, just what the customer needs to make that very specific. Would there be buses running between cities at that, price level? Probably not. Would there be the outskirts of cities? I mean, if you couldn't walk there, if you couldn't bike there, or maybe the subway could get you there, you wouldn't be living there. So the countryside would be basically abandoned. So in fact, the viability of technologies depends heavily on their pricing, and the price matters. And the very first way that launch affects satellite design is that it costs so much. And therefore, the mission has to be incredibly compelling. And so you can't just have Facebook in space, because it doesn't seem to be worth billions of dollars of investment to do something that's basically frivolous, that's basically for fun, that's basically to allow people to socialize. So we constrain ourselves in the space world to defense missions, to civil defense, which is really what weather is. We launch weather satellites because the justification is, what if there's some gigantic storm out over the ocean and we don't know anything about it? We have this weather satellite that goes, the old GOES satellites in the United States, one on the East Coast, one on the West Coast, watching for weather that otherwise couldn't be observed because the open ocean has very few observing stations in it, just some boats at sea and that sort of thing, sort of random, right? So we choose our missions based on that sort of a criteria. This has to be essentially of national importance, right? And it has to be of national importance to a nation that can actually afford it, which so far is not most of the nations in the world. Most nations in the world are not launching satellites into space because they just don't have the budget to do it, and the benefit isn't worth the cost.